Do great. Yeah, I think that's it.
All right, now that we fixed that. All right, just to catch everybody up on what we've been doing, for those of y'all at home who couldn't hear. We're trying to analyze this graph, right? And the first thing we're going to do is apply the first derivative test. First derivative test here. So we take the first derivative, we factor it out, and we find all of the zeros. Because this thing's a polynomial, so it will always have a solution. So we don't have to worry about the case where it does not exist. We just have to worry about the case where it's equal to 0. And we want to worry about that because these are going to correspond with our critical numbers. Okay? So we go through and we say we've got a critical number at 1, we've got a critical number at 4. And we break up our number line using those values, going from negative infinity to 1, 1 to 4, 4 to infinity. And then we choose an x value inside of each of those intervals that works for us. 0, 2, and 5. Then we plug those back into our first derivative, and we calculate what it comes out to be. When x is equal to 0, our first derivative is negative 4 cubed, which is negative 64. And our second derivative, at 2, we get 16. And our second derivative at 5 gives us 16. Now, before, there was a mistake that I had made in the calculation, and that was somewhat intentional, somewhat accidental. I had done the arithmetic in my head here and found that this was negative when it should have been positive. And that's just to highlight the fact that using a structure like this, it makes it a lot easier to identify where mistakes happen. But just because this method is easier to track back mistakes doesn't necessarily mean that we shouldn't go ahead and do the arithmetic by hand, right? Actually do those calculations. So then, now that we know that this is decreasing, increasing, and increasing on each of our intervals, now we move to the second derivative test, and that's where we're at now. Starting off by rewriting our first derivative, we then find our second derivative. We say, hey, we can factor out a 12, so let's go ahead and factor out that 12, and that is where I left off. This is x squared minus 6 plus 8. My mistake, 6x plus 8. This thing can be factored out even further into 12x times the quantity x minus 2 times x minus 4. Now we're going to apply the second derivative test. We're going to do that by taking this second derivative and setting it equal to 0. So f double prime at x is equal to 0. Well, when does that happen? That happens when x is equal to 2 and when x is equal to 4. Question, do we have any issues here? We have one, right? We have a critical number that corresponds with a possible inflection point. So we're gonna have to play with some things here, right? I'm jumping forward just to show what they've done after factoring this out. That is when they found the critical values at 1, 2, and 5. My mistake, 1, 2, and 4. 1 and 4. Wow, I can't talk today. And then they said, all right, we have at 2 a test point that we're using as well as a point of possible inflection. And at 4, we have a test point and a point of possible inflection. My mistake, we don't have a test point, we just have, yeah, we have a test point. It's 4 that is the critical number, isn't it? Yeah. Yeah. At 4, we have the critical number. Now we have to check here, and then we have to check in the second derivative test as well. Now, just quickly showing what the second derivative test looks like on its own. X is equal to 2, x is equal to 4, negative infinity to 2, 2 to 4, 4 to infinity, we're going to pick a value inside of each of these intervals that we like. Why don't we go ahead and stick with 0 here? Why don't we stick with 5 here? My mistake, 3 and 5 here. Now, plugging in 0 into our second derivative, this comes out to be negative 2 times negative 4, that's 8, times this 12. Well, that should come out to be 96, right? And that makes sense because look at what we've got up top, right? If x is 0, this term goes to 0. If x is 0 here, this term goes to 0. We're just left with that 96. Now coming over here, when x is equal to 3, our second derivative at 3 is equal to 1 times negative 1. This is going to come out to be negative 12. And then at f double prime at 5, this is going to come out to be 3 times 1 times 12. All of these are positive, and that's going to come out to be 36. So what does this tell us?
Decrease, decrease, increase.
It tells us something about the concavity, right?
Yes.
When we have a positive derivative, or positive second derivative, are we concave up or concave down? Should be up, right? Should be concave up. Notice what this tells us. We go from up to down at 2, so 2 is an inflection point. We go from down to up at 4, so 4 is an inflection point, corresponding with their solution as well. Yeah? Now, let's check this against the graph. Actually, before we check this against the graph, let's actually try to graph this out now. I'm going to graph that here in the middle. But before I do that, we're going to make a couple observations. Observation number 1. When x is equal to 0, our function is equal to 0. When x is equal to 1, using one of our critical numbers, we have 1 minus 12 plus 48 minus 64 so this is going to come out to be 60, my mistake, 72, 29 minus 76.
Negative 27.
Exactly. Negative 27. Just to keep all of this nice and neat, I'm going to go ahead and erase the arithmetic. 27. At 2, one of our inflection points, we really need to worry about it? Probably. It'd be a good idea to at least have a few points that we know, right? That way we can kind of connect the dots based on everything we know that has to happen in between them. Agreed? At 2, we should be higher because we're increasing now, right? So that's just something to know and check in advance. We know we should be somewhat higher. 2 to the 4th minus 12 times 2 to the 3rd plus 48 times 2 squared minus 64 times 2. I'm not going to even try to do this in my head. Does anybody have their calculator out?
Mm-hmm. 48.
Comes out to be 48.
No, I'm just typing it in.
Oh,
Negative 16.
negative 16?
So that's
Go.
about right.
Yeah, that sounds about right.
So that is increasing to negative 27. So
Right. And then checking at 4, throw that in as well.
checking at 4.
Should come out to be something large now, well, relatively large. I'm gonna guess in the 30s or 40s. No. Yeah, that sounds about reasonable.
0.
Oh, all right. Cool. Oh, yeah. I see why. 0.
Didn't we do that over there? No.
No.
Okay.
No. So our function at 4 is equal to 0.
Yes.
Now, we can come over, start graphing some things. Let me make this slightly better. All right. We know we have to go through the origin. We know at 1, we're down at 27. Negative 27, I mean. At 2, we're at negative 16. And at 4, we're at 0. Now we know that everything to the left of this blue dotted line is decreasing. Coming over to 4. we know everything is increasing. And after that, everything is increasing. Right? That's just from our first derivative test. Now, looking at our second derivative test, we know we're concave up before the first green line. We know we're concave down in between the two green lines. And we know we're concave up after the last green line. So this lets us start putting things together. I don't have a different color to really make this work well. So we know we're decreasing up to this point, right? Something like that. We're increasing now up to this point. Now we're concave down, so we have to have a bit of a slope through here, right? That way we can actually have that concave downward shape. So it's gonna look something like this. And through here, should do that like that. Get that inflection in there really well. There we go. Better. Now we're increasing back up, right? Let's make it a little bit better. So comparing this really quickly to what the actual graph is, pretty damn close. Pretty damn close, actually. We've been able to catch almost every detail of this function in here. Notice we do have a relative min at 1, -27. Which also happens to, in the interval shown on the board and on the PowerPoint, on the slides, it also happens to be the absolute min inside of that interval. We've got our 2 points of inflection. Remember, a point of inflection is when we change concavity. We've got our intercepts. We've got everything, right? Now, by looking at just those 4 points, we can kind of piece together what this graph already looked like, just from the little bit we know about polynomials. The real use in this is when you have more exotic functions, functions that are really chaotic looking, like cosines, tangents, combinations of exponentials with different weird powers, etc., etc., etc. For most of the problems that we have here in this class, if you know the way polynomials behave, you'll be able to graph them without using this method. But the point of this is to demonstrate, 1, how you could use derivatives. 2, it gives you an intuitive understanding of what a derivative is and tells you. 3, it sets you up to think in a more mathematical way of saying, based on what I know, given the very little bit of information I have, what can I get out of this? Well, you have just the function. You don't want to make a table of x, y points to graph it, so you can apply the derivative and get a bunch of information out of it relatively quickly. So having said all of that, let's keep chugging along. This is an example of another function that would be more chaotic, that the derivative, the graph isn't immediately obvious. I certainly have no idea what it looks like. Jumping to what that graph actually looks like this. Notice we've got a cusp up here at 0. So what does that tell you, just looking at this graph right here? What does that tell you about the derivatives? Yeah. Well, at x equal to 0, our first derivative looks like this. It looks like it might have actually been discontinuous. It turns out it's not. That I did not expect. I actually thought it was discontinuous at first. But again, just one application we can see where it might actually be useful. I am trying to get through this a little bit more quickly today, just so that we can jump to some older material that I put off until now. I thought this would be a good segue into it. Just a rule of thumb about what different functions look like. Y equal to a constant is just a straight line. Our slope-intercept form, again, another straight line, but this one's going to be slanted. Anything squared as the highest, or any polynomial of degree 2 is going to be a parabola. Of degree 3 is going to be this cubic shape. So just some things to know in advance, what different functions might look like. This will definitely help you when graphing this stuff. Having said that, before we get into section 3.8, I want us to touch on week 5.2 notes. Let me get to the right slide. Was it there? No, it was not. This was averages. Yeah. Multiple derivatives. Cool. Close that. Share screen. All right, now jumping into 5.2 notes and going back to section 2.7. Section 2.7 is all about this idea of implicit derivatives. Now, before we go and start talking about implicit derivatives, you should probably know what an explicit versus an implicit function is. An explicit function is exactly what it sounds like. It is a function that explicitly tells you how y behaves according to x. An implicit function says the two things are kind of related together, so you can't write a strict set of instructions that says y is equal to something with x. The two are somehow tied together so that you can't separate them out. That is what an implicit function is. So explicit, you can write strictly as y is equal to something in terms of x. Implicit, you can't untangle the two variables. So as an example of an explicit derivative, we've got this function y, or x times y is equal to 1. We're going to find an explicit derivative, but first we're going to find the explicit function. x times y is equal to 1, this tells us that y is equal to 1 over x. Okay. Now here, we can find explicitly what dy dx is. Just take the derivative. So y primed is equal to d dx of 1 over x, which is equal to negative 1 over x squared. And that's the explicit derivative, dy dx. So we're given a function which defines y implicitly with relation to x. We write it explicitly, and then we find the derivative in this particular case. But that's because we could. It's not always going to be the case that we can do that. An implicit derivative requires applications of the chain rule, as you can see there. And what we're going to do is we're going to start off by saying, well, let me back up. Let's just apply the chain rule to a couple of these first. The first function, we don't have to, right? This, you don't need to apply chain rule to differentiate. This, you do. And what's happening here is we're saying we assume that y is equal to some function of x. We have no clue what that function is. But if you notice, this looks a lot like the chain rule, right? Except instead of u, we're saying y. That's the only difference here. So if we take the derivative with respect to x of 2y cubed then what we should get is going to be something that uses the chain rule. It's going to come out to be the derivative of 2, let me write this out like this, dy 2y cubed times d dx of y. The chain rule, right? This is du dy, this is dy dx, giving du dx. This is assuming that we call y, let me say, this is assuming we call it 2y cubed u. Does this make sense what I mean? We're going to differentiate this u with respect to x. And in order to do that, we have to break this up using chain rule. First, we're going to differentiate the outside with respect to y, and then we're going to differentiate y with respect to x, and multiply the two together. Everybody cool with this? So what this should come out to be is going to be this first term is 6y squared. The second term, well, we can't actually define that explicitly, right? We're just going to have to write y primed. And that's it. This is equal to d dx of 2y cubed. Or you can write it as du dx. Is everybody cool with this? Okay, so what about C now? This was B. C, we're going to say that U is equal to X plus 3Y. So d dx of U is going to be equal to how do I want to say this? The first thing, this first term isn't going to have a derivative of y, right? So we can just go ahead and skip over it. We can say this is d dx of x plus d dx of 3y. D dx of x is 1 plus, well, this we're going to have to apply the chain rule to. D dy of 3y times d dx of y. Everybody cool with this?
1 plus, okay.
So what we're going to get then is 1 plus, this is going to come out to be 3, and this is going to come out to be y prime. Because we don't know explicitly what the derivative of y is with respect to x. Y prime. So C is going to be 1 plus 3y prime. Now, for this last term, we're saying that u is equal to x y squared. Well, this is like f of x times g of x, right? Everybody agree? So we're gonna have to use product rule here. Taking the derivative of u with respect to x is going to give us the derivative of x y squared with respect to x. This thing is going to come out to b. We have to apply the product rule. So y squared times the derivative of x with respect to x plus x times the derivative of y squared. Well, y squared, we're going to have to apply the chain rule to. Yeah, what's up?
You do d over dxu, and then d over dx xy squared, and then that's one thing, correct? And
Yeah, these are just two equivalent statements.
Okay,
Right? All I'm doing is saying, all right, I'm taking the derivative of u with respect to x. And u is equal to xy squared.
okay.
And now, because we know that xy squared is like f of x times g of x,
Yeah,
now we can see how to break this up.
okay, and
That's
so
all I'm saying.
okay, no, I just wanted to know my spacing to know, I didn't know if they were all connected or what, so,
No,
thank you.
equal. All right. So from here, we've got y squared times the derivative of x with respect to x. That's just 1. Plus x times, well, the derivative of y squared with respect to x, we're going to have to apply the chain rule again. This is going to be d dy of y squared times d dx of y. So we get y squared plus x times y squared differentiated with respect to y is going to be 2y. And y differentiated with respect to x is going to be y prime. So for d, the derivative should come out to be y squared plus x times 2y y prime. And each of these are equal to du dx. Where u, in this first case, was equal to x y squared. In the second case, it was equal to u was equal to x plus 3y. And in this last case, u was, or in this first case, u was equal to 2y cubed. All right, now let's jump to the next slide. Notice in A, we didn't need to use the chain rule. It just differentiated directly, right? You can pull out that constant, differentiate x squared to get 2x. 2x times 3 is 6x. In B, well, B, the first thing we have to notice is this is like c times u to the n, right? We're calling y some function u, essentially. Y'all can't see me at home, so I'm gonna have to stand over here to kind of explain it. So this is where we need to use the chain rule. Applying the chain rule, we got 2 times 3 times y squared dy dx. So what the hell is happening here? Well, this is the derivative with respect to y. And this is the derivative of y with respect to x. So this is du dy, and this is dy dx. Is everybody cool with that? Folks at home, does that make sense?
Yeah, sounds good.
Yeah, awesome. So notice really quickly some difference in notation. Instead of writing dy dx, I wrote y prime. That's because I'm lazy. Y prime is the same exact thing as dy dx, right? If f prime is equal to df dx, then y prime is equal to dy dx. Same exact notation. That's the only difference here. Jumping to the next example, well, the same exact thing happens. First, we take the derivative of u with respect to x, and we say, hey, we can break this up by that sum and difference rule. This differentiates directly with x. That's convenient. It just goes straight to 1. This, it doesn't. We can pull out the 3 and rewrite this now as dy dx. Or we could go about it using the chain rule in that longer approach like I showed. Excuse me. Now finally, in D is a little bit different, right? I wrote this backwards from what they have, y squared plus, I wrote 2y, they wrote 2x, times y times dy dx. But it's the exact same thing. If you notice what they've done here, they've just said, all right, well, we have to apply the product rule. And in one of these terms, we have to apply the chain rule. So applying the chain rule, we get to our solution. And that's really the whole gist here. We're going to do a couple more of these before I really let y'all off on your own. But like I said, part of the reason why I wanted to do the graph stuff first was to get more practice with derivatives. That way, when we came back to this stuff, we were a little bit more versed. Having said that, implicit differentiation. The easiest way to go about this, start off by writing both sides. The derivative, let me say this differently, I'm getting tongue-tied now. Start off by applying the derivative to both sides of your equal sign. Then go through and identify where you need to use the product rule or the quotient rule. Then figure out where you need to apply the chain rule and go ahead and write everything out in terms of the chain rule. Then differentiate with respect to x, and you're good to go. Is that cool with everyone? That's generally the way I would go about it. They have a slightly different set of instructions, a slightly different set of algorithmic approaches, but it's more or less the same idea. Once you've gotten the derivatives figured out, then you try to rearrange terms and solve for dy dx if you can. So to show what I mean, we've got this ellipse. This thing is going to look about like this. Nope, my mistake, I wrote that. Rotated. It's going to look about like that. Better centered, but about like this. This is the point 1, 0. This is the point -1, 0. This is the point 0, -4. This is the point 0, 4. And what we're looking for is the slope of the tangent line that is about here-ish. We're looking for the slope of that tangent line. All we know is that this equation, or this graph, can be derived, or is the result of this particular equation, x squared plus 4y squared. And I don't think the folks at home can see that, so let me use black again. 4 is equal to x squared plus 4y squared. Now we know the slope of our tangent line is equal to dy dx at, in this case, the points square root of 2, comma, -1 over the square root of 2. We know that the slope of this tangent line is equal to dy dx at square root of 2, -1 square root, -1 over square root of 2. So we have to apply the derivative to both sides of this thing now. Can't see green. So that is d dx of the constant 4 is equal to d dx of x squared plus 4y squared. Right away, we know something about this. The derivative of this thing is going to be 0, right? The derivative of 4, it just goes straight to 0. And on the right side, we can break this derivative up using the sum and difference rule. So d dx of x squared plus, we can pull out that 4 if we wanted to, 4 times d dx of y squared. This we can differentiate directly. This we're going to have to hit with the chain rule. So differentiating, we get 2x plus 4 times d dy of y squared times d dx of y. So now this we can differentiate directly because it's y squared differentiated with respect to y. That's going to become 2y. So now we're going to have 2x plus 4 times 2y times dy dx. All that is equal to 0. We're trying to solve for dy dx. So now we're going to have to subtract 2x from both sides, right? Because we have to solve for dy dx. So 0 is equal to 2x plus, simplifying this, we get 8y dy dx. Subtracting 2 from both sides, or my mistake, 2x. We get negative 2x is equal to 8y dy dx. Now all we have to do is divide both sides by 8y. We get negative 2x over 8y is equal to dy dx. Really quickly, notice we can simplify this some more, right? We can rewrite this as negative x over 4y. Yep. So this is what dy dx is equal to as a function. And we're given the point we want the tangent line to be at, right? Like we're given the point we want the line that is tangent to. That was this point right here. So we know xy is equal to the square root of 2, comma, negative 1 over square root of 2. We know dy dx is equal to negative x over 4y. So we know x is equal to square root of 2 divided by negative, my mistake, 4 times negative 1 over square root of 2, which we can simplify now. The negatives cancel, and we can bring the square root of 2 up top to get 2 over 4, or just 1/2. So this thing is equal to 1/2. Let's check it. Oh, I did draw it the right way the first time. My mistake. That happens. This is why you shouldn't second guess yourself, because you usually do have it right the first time. But what we just found was the slope of a line tangent to this point. For folks at home, that is the line tangent to this point right here. We just found the slope of this line. Going through everything, first, rewriting our function, our equation, x squared plus 4y squared is equal to 4. Apply the derivative to both sides. We know the derivative of a constant is going to be 0. Applying now the sum and difference rule, the constant rule, and then the chain rule, we get this. This is just implicit differentiation is what we're doing here. Then we want to solve for dy dx. So we subtract 2x from both sides, divide by 8y. dy dx is equal to negative x over 4y. So from here, we just want to plug in our points. We know what x and y are, so let's just plug them in. Plugging them in, we get 1/2. Having said that, I will let y'all take a quick 10-minute break. We'll come back to some more problems.